Let us start this lecture by quoting a thought process from Arthur C. Clarke. He says, when a grey bearded scientist says that something is possible, believe him. When he says that it is impossible, he is likely to be wrong. That means, you need not to follow anybody blindly. And I remember that Swami Vivekananda has told, impossible is a word found in Fool's Dictionary. So therefore, one should not just accept, that kind of things. Then only the science can progress, so also the engineering. So if you look at, we have discussed a lot about the heat engines, by various thermodynamic cycles we have discussed, starting from the Rankine vapor cycle, and then of course we have looked at regenerative, reheat, and then what we call superheated steam, the superheated Rankine cycles. Later on we moved to the gas power cycles. Under that we had discussed about Otto cycle, diesel cycle, dual cycles, and also the Brayton cycle, like which will be catering to various heat engines developed by us for meeting our power requirement. Today we will be discussing about the other one, that is the refrigeration cycle, which is just opposite of the heat engine. And so if you look at question arises, what do you mean by refrigeration? We all use refrigerator in our home, and in particular in summer we use air conditioning systems, and that is basically a process of maintaining certain region at low temperature as compared to the surrounding temperature or the ambient temperature. For example, in summer it is very hot, so we need to keep our room cool, and then you can use the refrigerator. We need to use the air conditioner, but suppose you want to keep some food at the lower temperature, or the vegetables or the fruits, then we will have to use the refrigerator and other things. And in other words, basically what is being done here, the heat being transferred from lower temperature region to the high temperature region. Of course, you need to provide some amount of work, and when we do that, we call it as a refrigeration. And it is a basically, if you look at a refrigerator, is a device that produces the refrigeration effect or the cooling effect, you can say that way. And air conditioning is little different. It is not only the what we call produce the cooling effect, but it also the condition the air, means quality of the air it has to control. So we will be discussing about basically refrigeration cycle, the cycle which is used for analyzing or the cycle which is used for the refrigeration system, right? We call it as a refrigeration cycle. In other words, basically the refrigeration system operates on this cycle, right? So if you look at what are the common application of the refrigeration systems, of course, as I told you, that your what you call the air conditioning systems, refrigerators we use for cooling the food and other materials, like which are easily get spoiled by the factory and other things, and any other things we use. So there are, you might have seen on the way to our academic campus, that there is a nitrogen, liquid nitrogen plant, right? And liquid hydrogen plant. You must have seen, right? And they are also use the refrigeration system, and I would suggest that you can go and check what is happening here and what is being covered in the class. So, if you look at the common application of the refrigeration systems are refrigerators and air conditioner, heat pump, gas separator. We want to separate the gas. Let's say, from air, I want to separate nitrogen or the oxygen. I can go for low temperature, convert into liquid, and then I can separate. And ice production is a very age-old thing, right? And liquefaction of the gases, we do that. For example, like we use, liquid hydrogen and liquid oxygen in our spacecraft, rocket engines, cryogenic engines, right? So, and several other places we can use that. So, it's a very important, application. And in this, all these things, we use a, fluid which will having certain properties, and that we call refrigerants. There are various kinds of refrigerant. We will be discussing about that, but it will be having certain properties which is not same as that of the other fluids, right? As we had seen that certain fluids are being preferred for the heat engine. Similarly, certain fluids are preferred for the refrigerant system or refrigeration system, and that we call refrigerants. And so, if you look at what is the difference between the refrigerator and heat pump, if you recall, we had already discussed about it. Basically, refrigerator will be taking the heat from the cold region, right, and giving to the hot regions, whereas it is other way around, right. The heat pump will be taking the heat from the hot regions and then giving to the cold regions, like in winter we use the heat pump, right. So, as I told that already, that refrigerator is basically to remove the heat QL from the cold medium or the cold region, and the heat pump is to supply the heat to the warm region, right. And because the winter we use, and that is warm, and we will be giving some heat to the warm region. So, if you look at this is diametric, schematically shown here, that is in the cold region, in case space, we take some amount of heat QL, and that is the desired output, and then we will give some work input here, and then we will reject QH amount to the warm region in case of refrigerator. But whereas the heat pump, it is other way around, it takes certain amount of heat QL from the cold region, and it supplies the QH amount of heat in the warm region, which need to be maintained properly in the winter season, right. And of course, you will have to give some work input to the heat pump. And of course, how to characterize the performance of refrigerator and heat pump? In case of the heat engine, we use the thermal efficiency, or of course, we can also use the second law of efficiency, just to check whether how good or bad it is, or what are the other scopes of enhancing the thermal efficiency of a heat engine. But in this case, we will be using the coefficient of performance, right. And that coefficient of performance for the refrigerator is nothing but your cooling effect, and divided by the work input, right. And of course, if you look at this, the net work input will be basically QH minus QL, right. And similarly, for the heat pump, it is other way around. We take the heating effect, right, that is nothing but your QH, right, and net work done, that is the ratio, the coefficient of performance for the heat pump is the ratio of the heating effect divided by the work input, right. And if you look at the difference between the refrigerator and the heat pump is that in one case the desired effect in case of refrigerator is the cooling effect QL, and for the heat pump the desired effect is the heating effect, that is QH. So what we will do, we will have to look at our Carnot cycle in a reverse way. In this case, what is being done is that you compress the, of course, the fluid coming from the evaporator, and then you will have to condense and reject QH amount of it to the what you call in the hot region, and then you will have to like the refrigerant will pass to the turbine where it will be expanded, and then it will be going to the evaporator where it will be absorbing certain amount of heat from the cold region. So if you look at this is basically your cold region, right? And keep in mind that we don't really use the turbine, but here I have just saying that is expansion. And in real situation we will be using basically what we call capillary tubes or the throttling valves we have already discussed. Let us look at here what is happening. In this case, if you look at 1 to 2 is your compression. This is the two-phase flow kind of things, and 1 to 2, and here 2 to 3 is your heat rejection in the condenser, and 3 to 4 is your expansion. Of course, we are considering isentropic expansion 3 to 4, and then 4 to 1 is your heat being what you call taken from the cold region by the evaporators kind of thing. So if you look at 1 to 2 and 3 to 4 are isentropic process, and of course this is the two-phase fluid. So therefore the heat heat absorbed by the evaporators and heat rejected by the condenser are isothermal, are isothermal in nature. The process heat transfer is isothermal. So of course this is the ideal case, which is not really possible to implement. It is because of, as I told, that it will be two-phase fluid. It is very difficult to compress the two-phase fluid, and also the says that it will be reaching the saturated vapor line, right? And also similarly the expansion from the state 3 to 4 is also difficult because it is passing through basically two-phase fluid. Of course, it started with the saturated liquid, but after that it became a two-phase fluid, which will be very difficult to do that, and it will be spoiling the turbine blades and other thing. So of course you can get the Carnot basically coefficient of performance for the refrigerator, that is TL divided by TH minus TL, and for heat pump it will be just TL here in the refrigerator system coefficient of performance will be replaced by the TH, right, and rest is the TH minus TL. Therefore the the difference between the COP of refrigerator and the heat pump is that only the your desired things are different. In one case it is TL, another case TH. So as I told that reverse Carnot cycle is not really possible practically. Now we will have to change the components or the process such that it is you can implement it very easily. And if you look at, as I told earlier, that this turbine can be replaced by a throttling valve, and we use capillary tube in case of refrigerator and other devices also. So the ideal like the vapor compression refrigeration cycle, because here we are basically compressing the vapor, and once it is passing through the evaporator, like kind of things. So evaporator, it is the vapor one, and then ideally we can say that it is saturated vapor condition, and then you can what you call compress it isentropically to 2, and then heat will be rejected in the condenser, that is the condenser 2 to 3, it will be rejected to the warm environment, and that is QH. And then after that what will happen, like we can call basically 3 to 4 that dash is isentropical expansion, right? But however, in the real situation it will be isenthalpic process, that is 3 to 4, right, which is will be taking place. So this is the ideal what you call vapor compression cycle. And if you look at if you compare the ideal vapor compression refrigeration cycle with the Carnot cycle, it is heat rejection, and what you call in the 2 to 3 is the same constant what you call temperature heat rejection, and only thing is that difference what you could see, it is the superheated vapor here in the station 3, and then of course it comes to saturated condition, but however the what you call in this region, right, what you call the temperature remaining constant, but however if you look at it is the isobaric heat rejections, right, the pressure will be remaining constant, this is the line, and the heat absorption by the evaporator is basically also the isobaric 4 to 1, and it is, if you look at, if I could manage to keep it here in this two-phase flow, so this will be also isothermal in nature, right. So in case of heat rejection, it is only 3 to, you can say this is 2 dash, like it is only those portion is isothermal, but it is not, because temperature is changing. But however, this what you call heat rejection and the heat absorption are isobaric process, and 3 to 4 is your isenthalpic process, right. And that is the difference, but whereas it is 3 to 4 dash is basically in case of Carnot engine, that is isentropic process, and of course 1 to 2 is also the isentropic compression, but in case of Carnot engine it is basically two-phase fluid to the saturated vapor condition. It is case of reference system, it is going from the saturated vapor to the superheated vapor state during the isentropic compression. So if you look at the same thing, we can see in the P and H diagram, right. It is will be very clear. I mean, like the 3 to 4 is basically isenthalpic expansion, right, because why? H3 is equal to H4, and of course 2 to 3 your heat what you call rejection, that is the QH, is the constant pressure heat rejection, and 1 to 2 3 is isentropic compression, and 4 to 1 is your again isobaric heat absorption. So we can analyze this thing. What we will have to do, we will have to use the first law of thermodynamics, and we know that is QL amount for the process 4 to 1, right, which is nothing but your H1 minus H4, and we do the same assumptions here, that is the flow is steady process and there is a change in kinetic energy, and is equal to 0, and change in potential energy is 0, and there is no shaft work here in this case is 0. So for process 4 to 1, and it is a steady flow process, all the things, so we will be using that. So QL is equal to H1 minus H4, and similarly we can get W in, or the what you call the compressor work. This you can say this is basically work input to the compressor, right, and which is equal to S2 minus H1, right. And COP of refrigeration, if you look at QL divided by WC, that is you can say this is basically input to the compression, right, that is equal to H1 minus H4 divided by S2 minus H1. And we have seen that there is no work being produced by the expansion process because of throttling process, right. S3 is equal to H4. And question is this throttling process reversible? Certainly no. We have already seen that entropy is increasing during the throttling process. So as the S4 is greater than the S3, so therefore it is an irreversible process. But for the reversible process, S4 dash is equal to S3, that we have seen, right. Of course, you cannot see in PS diagram and TS diagram, right one. So therefore the amount of heat which is absorbed during the reversible process is equal to H1 minus H4 dash. So if you look at that, will be what you call higher as compared to the irreversible process, that is the throttling process. So therefore loss in refrigeration per unit mass will be nothing but your H4 minus H4 dash, right. That will be the loss in refrigeration per unit mass due to the isenthalpic process in a what you call throttling valve or a capillary tube, what we use it. So question arises how to choose a refrigerant, right, because that means we need to look at the properties what it should have, then only. For example, you can say, can I use a water as a refrigerant? Can I use air as a refrigerant, right? Can I use, because these are the two fluid which we are very familiar with, but of course that can be used, and we'll see later on that we will be using air for as a refrigerant, as a fluid for the refrigeration system, which is being used particularly for your aircraft applications. We'll see that. And for a refrigerant, the boiling point of a refrigerant must be lower than the temperature of the evaporator, because that is should be there, otherwise you cannot really absorb the heat, right. And critical pressure must be high enough such that the phase change occurs in the condenser, because the condenser, the phase change will be occurring, otherwise it is not possible to give the heat to the out, like heat rejection is very important. So suppose you are having a refrigerant whose critical pressure is very low, then what will happen? It cannot, it will be remaining in the vapor state. So therefore particularly the vapor compression cycle, you cannot use it, right. And it must be non-toxic and non-corrosive also, because it will be passing through the various components. It will corrosive means it will be eroding the material, and the life of the refrigerant system will be refrigeration system will be very less or very low. And it will be non-flammable, because if there is a leakage, then there will be problem of getting what you call burnt, or some fire will be there. So therefore it will be non-flammable, and of course it will be cheaper, and there are other properties one can look at it. So it must remain chemically stable while undergoing the cycle, because in the cycle various processes are taking place, like it is getting evaporated, it is getting condensed, so it will be stable chemically. If it is changing its chemical properties, then it will be problematic, and it will lose the refrigeration properties. So what are the common refrigerants? If you look at there are several of them. I will be discussing few of them only, because If you look at the oldest of refrigerants is the ethyl ether. You must have used the ether, it evaporates very easily and cools down, right, that we use. And but of course later on the ammonia and methyl chloride, ethyl chloride, sulfur dioxide, several of them are being used. And generally the ammonia is, although toxic in nature, but it is very much preferred in industrial applications because of the fact that it will be having higher COP, right? Coefficient of performance will be higher, so that the cost will be lower, like that is the but of course one can use hydrocarbons like propane, butane, gasoline, ethane, ethylene, several of them one can use as a refrigerant, but those are not being used because most of them are flammable in nature, like. But this CFC which are being used earlier days, which were rather being used earlier days, that is the chlorofluorocarbons, and if you look at there are 3 of them which are being used, R11, R12 and R22, and several others also, R115, and then other things will be R105. So there are several of them. I have just given 3 examples. R12 is being used basically for your domestic applications, and R22 is domestic means refrigerant kind of things. Refrigerator it is being used, and R22 is being used in your air conditioning system. And these are the causes of this what you call the ozone layer depletion. So therefore that is being banned across the world, and then of course nowadays people are going for chlorine free fluorocarbon, that is R134A. And of course there is other varieties like Freon 12, that is difluoromethane, and other things which are being used, right. So nowadays people are using basically R134A, and there are several variants are there, and it is being sold in various places in a different names, right. So if you look at there is a urgent need to have developing a refrigerants which will be benign, kind of things, and also serve the purpose. So and it should not spoil the ozone layer, nor the pollution or the other aspects. So that is an important one what research people are doing. So we will take an example like basically to illustrate that how to calculate. This is an ideal, in an ideal vapor compression refrigeration cycle, 1.2 kg per second of this tetrafluoroethane, that is R134A, as a refrigerant is used to maintain the cold region of minus 8 degrees Celsius, right. And its saturated vapor enters into the compressor at minus 10 degrees Celsius and leaves the condenser at 40 degrees Celsius, and determine the compressor work and the refrigeration capacity, and of course the COP of this cycle, ideal cycle, what will be finding out. If you look at like basically this is operating at the this temperature, if you look at this is your basically the minus 8 degrees Celsius kind of things here, like because it is refrigerant used to maintain cold region, that is 8 degrees Celsius, right. And it the region is in a cold, and then saturated vapor enters into the compressor at minus, that means this is T1 is basically minus 10 degrees Celsius, and leaves the condenser, right. If you look at condenser is this one 3, right, at 40 degrees Celsius, right. This is basically T3, you can say 40 degrees Celsius kind of things. So what we will do, we will have to use basically refrigerant table, like to get these properties and then try to solve this problem. So if you look at what are the things are given here, like as I told, the T1 is given as minus 10 degrees Celsius and T3 is 40 degrees Celsius, and the mass flow of the refrigerant is given 1.2 kg per second, and we need to find is the work done by the compressor and what you call the refrigeration capacity, that is QL, and COP of refrigerant, right. So what we will do, we will basically look at the refrigerant table corresponding to minus 10 degrees Celsius. So we can use R134A table, right, at minus 100 degrees Celsius. What we will get? We will get H1 is equal to Hg, right. This is at the saturated vapor line. So that I will get basically 392.2 kilojoule per kg, and we will get Sg, which is equal to S1 is 1.7319 kilojoule per kg Kelvin. And the pressure, if you look at, I can get the pressure P1, that is saturated pressure, is 201.7 kilopascal. Similarly, at 40 degrees Celsius, right, we will get basically this data, right. P3 is 1017 kilopascal, and HF, which is equal to H3, 256.54 kilojoule per kg, and S3 is equal to SF, right, that is equal to 1.1909 kilojoule per kg Kelvin. And Sg, I can get that Sg is equal to 1.721723 kilojoule per kg Kelvin. So we need to find out the compressor work, and that is basically Wc is equal to m dot S2 minus H1, right. So if you look at H1, we know, right, H1 is known, so this is known, right, and S2 we need to find out, and m dot already is given, this is given, this is given, S2 we will have to find out. So how I will find out S2? Because the process is isentropic, right, here. So I know this entropy at this point, right, S1. So if you look at the process 1 to 2 is isentropic, right, that is the isentropic compression, right. So therefore, that means S1 is equal to S2, right. And we need to use basically what you call the what will we know this S1, right, that is equal to 1.73 1.7319 kilojoule per kg Kelvin. And from this what you call 40 degrees Celsius, right, we can find out this SF, right, this SF, we can find out also the SG, right, and if you look at this SG is basically less than the S2. That means what? That means it is basically the superheated vapor, a refrigerant, right. So, as the S2 is greater than the SG at 40 degrees Celsius, right. Okay. So, therefore, the state 2 is at superheated condition. So, from the superheated steam table, superheated refrigerant table, right, R134A, we can find out, right, I mean we can match this S2 is equal to S1, and that is happening at the pressure, right, of 1017 kilopascals, right. And once we can find out that, then we can find out corresponding this table, S2 is equal to 1.7319, and right, we can find out the temperature also, like by interpolation, that is 44.94 degrees Celsius, right. And if you know, like if you look at this pressure is already given, like P3, this is the same constant pressure process. So, by that, by mapping this S to S1, you can basically find out what will be the temperature. Temperature happens to be here 44.94 degrees Celsius, and correspondingly S2 we can find out, that is 4 to 5.68 kilojoule per kg. And once you know these values, what you can substitute these values here, 1.2 into 4 to 5.68 minus H1 is your 392.2. So, that will be happening, like if you do that, you will get something 40.08 kilowatt. Okay. This will be giving you this much of amount of work has to be given to the compressor. So, if you look at, like we have already seen S3 is basically H4, right, and we need to find out basically the what you call refrigerant capacity, that is Q dot L is equal to m dot into H1 minus H4. So, we know that for process process 3 to 4 is basically isenthalpic process. So, S3 is equal to H4. So, S3 already we know that is 256.54 kilojoule per kg, right. H1 already we know. So, therefore, you can very easily calculate that, because m dot is 1.2. H1 is basically 392.2 minus H4 is 256 0.54. So that is equal to 162.89 kilowatt. Right. So what now we need to find out basically COP, that is coefficient of performance of refrigerant, that is Q dot L divided by W C. So Q dot L we have already found out, that is 162.89 divided by the WC. WC is basically 40.08, and you will get 4.06. But if you consider between these two temperature, the Carnot, reverse Carnot cycle, then we will get the COP of Carnot is equal to TL TH minus TL, which is equal to basically, if you look at this, is 263 divided by the 50, and that is equal to 5.26. So you can note from here that COP of the Carnot refrigeration cycle is greater than the COP of the ideal vapor compression cycle. So I mean, by this one can really learn how to calculate and how to do that. And let us now discuss about actual vapor compression refrigeration cycle. Earlier we had discussed the ideal vapor compression refrigeration cycle, because of fact that the processes in the compressor need not to be isentropic in nature, and so also during the heat rejection we have considered isobaric process, and heat absorption also isobaric process in case of ideal refrigeration cycle, but that won't be possible in actual situation. So let us if look at the component wise, it will be having the similar, like a evaporator and a compressor, condenser, and the throttling valve, or the what we call expansion valve. But the process in the compressor basically will be non-isentropic in nature, that is 1 to 2. If you consider this, basically entropy has increased in this case. In the ideal situation, the entropy will be remaining constant. That means for isentropic compression, that S3 is equal to S1, and for actual compression for process 1 to 2, right, that S2 is greater than S1. And in certain cases also we can intercool the compressor so that entropy will change, the process 1 to 2 dash. Of course, that is to what you call enhance the COP, coefficient of performance of the refrigerator. And as I told that in condenser there will be a lot of tubes will be there, and I will show you maybe actual refrigerator. And so also in the evaporator there will be a lot of tubes will be there, and then losses will be very high. And generally this expansion valve is very closer to the evaporator, and then we will see just after this discussion. And as a result, the pressure in the condenser won't be remaining constant, and as the pressure is not changing in the condenser, so also the temperature during this two-phase flow will be changing. That means it will be lowering down. So pressure is lowered down, so also the dashed line what I have shown here is basically ideal process. This is ideal, right, and this solid line is actual process, right. So therefore, the process will be to the T4 point in supposed to be, but however, it is very difficult to maintain the liquid what you call saturated vapor at the end of the condenser. Therefore, it is will be helpful to go for the subcooled liquid till the state 5, which is the liquid. And it is also a requirement for the expansion or the throttling process, because of fact that if it is not saturated liquid, then enthalpy will be change won't remain constant. Therefore, if it is subcooled liquid, so that it will be remaining constant. So H5 is equal to basically H6 in this case. And in as I told like earlier, that there will be what you call pressure change in the evaporator also. So therefore, the process is little bit extended from S6 to S7. So in this process, what is happening? Basically, you will have to give more work input to the compressor, and the cooling effect also being reduced. As a result, like COP will be lower in case of actual vapor compression refrigeration cycle as compared to the ideal one, and which is expected. We have seen also in the case of heat engine, thermal efficiency of actual cycle is lower than the ideal cycle, right. So let us look at a household refrigerator system. So this is your compressor, which is shown, right. This is the hermetically sealed compressor, what people use it, and there is a condenser coil. If you look at, you might have seen, very old refrigerator system which is not covered. Nowadays they have covered. If you put your hand, it is very hot. You might have observed, right? Did you see any time? Go back to or even side, and this a lot of tubes. Therefore, the pressure losses will be there. And this is your capillary tube, what we call it as a throttling valve or expansion valve. This is very simple, very what you call hypodermic tube can use as a small diameter tubes, very simple one, and which is closer to the evaporator coil and which will be remaining in your freezer compartment, right. And that is maintained around minus 18 degrees Celsius from where the heat will be absorbed, and then it will be passing through. And of course, the other places the temperature maintained around 3 degrees Celsius in your household refrigerators, okay, not your other refrigerator where the low temperature is being used for keeping the ice cream and everything. Therefore, it is important to keep ice cream and other things, like a freezer compartment. Otherwise, it will be melt out. So this is the typical kind of things what will be, being used. Of course, the liquefaction systems and other things will be, you want to have a what you call the much lower temperatures, and you may not achieve with the same refrigerant. You may use some different refrigerants also together, and that is known as cascading refrigeration system kind of things, which we won't be discussing. But however, if you are interested, you can look at it. But as I told, that whether this air conditioner which is used can be used for heating in the winter season, heat pump. Because all the systems are similar, like if you look at, this is by having what you call expansion form valve, and it is your compressor, and this is your what you call the indoor coil kind of thing which is there, and this is your outdoor. You can say this is your, sometimes it will be acting as a condenser, and it will be acting as also a evaporator. So you just change. This is one of them, like this. So in this case, what is happening? In this case, we are using this as a heating mode. That means we are taking out, this is your indoor which is fixed in the room, right? And what is happening here? It is compressed. If it is compressed here, then it will be what you call higher temperature, right? And so that it will be taking or giving the heat out here, right? QH, isn't it? And then it will be coming and expanded, it will be lower temperature, and again it will go back and what you call absorb the heat from outside, QL. And then it will go to again compress and go. That means it will be acting as a heat pump mode. Now, if you look at it is other way around, that it will be acting as a cooling mode. Heat pump will be acting as a cooling mode. The air conditioner, what do we say, air cooler you can say. And in this case, it is the compressor, right? It will be compressed, and this valve will just reverse. It is other way. Now, instead of going to the indoor, it is going to the outside door, right? In this case, it will be giving out heat here. This will be acting like a what? Condenser here now, right? In this space, it will be a condenser, right? And then after that, it will come and it will be expanded, and it will be like a what you call evaporator kind of things. And again, after that, it will go to the again compressor, and it will compress, and the cycle is complete. So this will be, if you look at, it will be acting like a evaporator, and it will be giving what you call taking heat from here, QL amount, right? So you just use this reversing valve, and you can operate your air cooler as a heat pump in the winter season and air cooler in the summer season. So this is a very simple techniques which is being used. One can go for it. So if you look at, we have looked at these vapor compression cycles. Of course, there is a vapor absorption cycle which we have not discussed, but there is a simple gas refrigeration cycle which is being used, which will be using the gas, not the vapor, like your kind of things. And in this case, what is happening? Again, it will be compressed 1 to 2, and there will be heat exchanger, heat will be going out, and then it will be expanded in the turbine, and then heat exchange, so that amount of heat will be taking from the what you call cold region to that, and then it will be, heat is rejected. So if you look at the processes, and this one is known as reverse Brayton cycle. We have already looked at Brayton cycle for generating power. It is just opposite of that. That is, if you look at 1 to 2 process, basically isentropic, right, what you call compression, and 2 to 3 process is what you call heat rejection kind of things, right, and 3 to 4 is again isentropic expansion, this is in the turbine, and 4 to 1 is your heat absorption from the cold medium, right. And as a result, we are getting, we're just reversing the other way around, and then using that. So this is the ideal, gas refrigeration cycle. If you look at, we will be discussing about ideal, simple, ideal gas refrigeration. There is also complexity involved in it, which we won't be discussing. So what we are looking at here now, basically, the ideal reverse Brayton cycle, and we need to analyze it, and we will have to apply the first law of thermodynamics for each components. For example, for the process 4 to 1, where heat will be absorbed, that is QL, which is nothing but is equal to H1 minus H4. We will be making the same assumption, the steady flow process in this case, and change in kinetic energy is 0, change in potential energy is 0. So therefore, QL will be equal to H1 minus H4. Similarly, QH will be equal to S2 minus S3. The same thing, like. So, and the work is basically by the turbine. See, if you look at here, the turbine is being produced some work, right? S3 minus H4, right? And compressor is S2 minus H1, and net work will be WC minus WT, and that you will have to, is equal to S2 minus H1 minus S3 minus H4. And if you look at the COP, coefficient of performance, is nothing but QL divided by W net, and you can find, we are assuming that Cp is remaining constant. Therefore, we can express this enthalpy in terms of temperature, because Cp is remaining constant, but it won't be. For our assumption, we are saying Cp is constant, is not changing with respect to temperature. In actual situation, it would be. This is ideal we are taking, and ideal gas also we are assuming. So, therefore, it becomes T1, the coefficient of performance of these gas refrigerators will become T1 minus T4 divided by the what you call difference, that is T2 minus T1 minus the bracket T3 minus T4. So, that is the thing. If you look at this COP of gas refrigeration will be less than the COP of vapor compression refrigeration cycle. I mean, you can do a simple calculation and you can see that whenever it is operating between two temperatures, this will be lower. So, it uses for aircraft cooling, liquefaction of the gases, of course cryogenic systems, and don't think that this is the use so simple cycles. But there will be varieties or complexities will be involved in that, in the sense regenerative and other things are being used so that COP can be enhanced. So, if you look at, we have given you an overall view of the refrigeration cycle kind of things, and we will be now stop over here and we will be discussing in the next lecture basically about how to handle these mixtures and how to handle the properties of the what you call air, because air conditioning we will be looking at. So, we will be looking at such that we will learn that. Thank you very much.